Okay, another thing, guys, to be aware of, you might want to write this down. Obviously, this week we are at school on Friday, and you will have your first quiz. Okay, the practice quizzes to do are chemistry quizzes 1, 2, and 3. Okay, remember that that is in Google Classroom. Okay, so if you go into Google Classroom, okay, for period 1, okay, in your classwork tab, okay, it's right here, practice quizzes and solutions. Okay, you just click on that, and you can look at chemistry quizzes 1, 2, and 3. Okay, I would say hold off probably on 2 and 3. Don't do them tonight because it's on naming, and we're just starting that today. Okay, but definitely have a look at quiz number 1. That's all the atom stuff that we'll be going over. Okay, and remember that the solutions are down at the bottom. Okay, if you click on that, it'll take you to the YouTube channel, okay, where you can find the solutions video for each of those 3 quizzes. Okay, so maybe try one tonight, check the video, see how you do, and then come in and see me for help. Okay, also new this morning, I put my help times up. Okay, so you can come in and see me for help, okay, in the mornings from 8:05 to 8:25, Monday, Wednesday, and Thursday. Okay, you can come in and see me at scheduled help Monday, Tuesday, and Thursday. I can't do Wednesday because I'm on supervision, okay, and there's no scheduled help on Friday. You can come and see me every day at lunch. Okay, I'm always here because I have no life. Okay, so you can come and ask questions. And you can also see me Monday, Wednesdays, and Thursdays after school until about 4 o'clock. Okay, so lots of opportunities to come in and see me for help if you need some, and there is no shame in doing that. In fact, it's pretty smart to do so. Okay, so please come in and ask. You're not bothering me if you're asking questions. I like answering questions. Okay. All right, so let's go over these questions from Friday. Okay, so question number 1, who first proposed the idea of the atom? Democritus, right, okay, the Greek guy. And it was rejected because?
Aristotle said that everything was made up in 4 elements.
Right, a better respected or more respected thinker said 4 elements, everybody liked that idea better. Okay, popularity won out. That was the one they went with. Okay, what were the 4 elements? Sorry, I think you said earth, air, fire, and water. Okay, those are the 4 elements. Okay, and it made sense because they could say, you know, everything was a mixture of this and that. Okay, I think the example I used in class was things like steam would be some parts water, some parts fire, and some parts air. Okay, things like that. It made a lot of sense to them. It was something kind of that you know, tactile that they could see, feel, and understand. Okay, for number 3, who was the group in the Middle Ages who inadvertently did a lot of work? The alchemists, yeah, okay. And what were they trying to do? Right, get rich, turn red into gold, find some sort of drink that would make you live forever, okay, all of that kind of stuff. Okay, so, late 1700s, who was the guy who came up with an idea on the structure of matter? Probably the most important person.
John Dalton.
John Dalton, yeah. John Dalton came up with the atomic theory, okay? The 4 points of the atomic theory, okay, are as follows. And you don't have to quote them exactly as they are in the notes, okay? You can put them in your own words as long as they have kind of the following key points. Okay, so if we are looking at, okay, point number 1, okay, very simply, all matter is made of atoms. Okay, we don't have to say tiny indivisible particles called atoms. We can shorten it. Okay, that's the most important part. The most important part is all matter is made of atoms. Okay. Point number 2 has to do with atoms of the same element being identical. Right. Okay, and of course you can add on to that different atoms are different. I mean, that's different elements have different atoms. That's fine too. Okay, point number 3. There's a couple of keywords that have to be in this one. Okay, this describes how molecules and compounds are formed. Okay, so atoms can combine in whole numbers. Okay, it has to be whole numbers. Okay, I can't have fractions of an atom, okay, in a chemical reaction. Did you sign in at the office?
Yeah.
Thank you. Did you bring me a sheet?
No, they said they didn't have anything.
Oh, okay. All right. Questions on point number 3? Okay. Point number 4. Okay. This one was the one that said you can't turn lead into gold. Okay. So in a reaction, okay, by the way, this is shorthand. Sometimes I use shorthand. RXN is reaction, short for reaction. Okay. Okay, so if we're kind of summarizing that one, in a chemical reaction, atoms can be separated, they can be joined, they can be rearranged, but they can't be changed. Okay, I can't turn lead into gold. Okay, I believe I said this last week, but I'll say it again, and you'll see it in one of the practice quizzes. I will ask you to write the 4 points of Dalton's atomic theory in your own words, so make sure you've got those kind of key points in there. Okay. All right. Okay, looking at this theory now, what things do we know of that might not be 100% true? Anything? What can we do that Dalton said we couldn't? Atoms are indivisible, right? Which means he said you can't split them. Now, he meant, of course, in a chemical reaction. That is still true, but atoms are divisible if you have the right technology. Okay, we can definitely split atoms. Okay, the other thing he said was atoms of the same element are identical. That's true in the number of protons. It is not always true in the number of, can sometimes be, yeah, if they get charged, they can lose electrons for sure. I'm thinking more in the nucleus. Neutrons, yeah, we could have isotopes that have more neutrons or less neutrons than the most common form. Okay, there are very few elements, okay, where there's more than about 3% of their atoms that are actually isotopes. Okay, so like if we look at carbon-14, like 99% of all carbon is carbon-12. 1% is carbon-14. Okay, they're not common. Okay, but so it's still essentially true. Okay, for number 6, describe in your own words the models of the atom described here. Okay, give a brief explanation as to why each has been rejected over the years. So you should have some progression on your sheet that says solid sphere. Okay, Dalton's solid sphere. And then you can say rejected when Thomson discovered electrons. Plum pudding model. Okay, rejected with the discovery of protons. Okay. Then you could probably go from there straight to the nuclear model, okay, which is Rutherford, and the gold foil experiment. Okay, so maybe something like this. So you could go Okay, that's greatly simplified, but it could be used to help you review your stuff. Okay, those are basically the models that we talked about. We had the solid sphere by Dalton, the discovery of electrons by Thomson, rejected that. Thomson came up with plum pudding. Protons and neutrons were discovered, rejected that. Rutherford did the gold foil experiment, proved the nucleus existed. Bohr tried to explain where the electrons go, but that was rejected when we found out electrons can jump. De Broglie's electron cloud model explains everything that we know at this point. Okay? That just follows the progression in your notes. Okay, is it possible our current model could change? Absolutely. Okay, we're always discovering new things. The Large Hadron Collider told us a lot about the structure of matter. Okay, it's very possible that our idea could change, especially when we start talking about quantum mechanics and things like that. Okay, it's very possible. Everybody believes that at the time what they're looking at is right. Okay, it's the change part that's hard. Okay, I'll give you an example. Right, when I was in high school, okay, they were, and remember that when I was in high school, tablets were something you wrote commandments on. Okay, like they were stone big. Okay, at that time they were just transitioning from all life on Earth fits into two kingdoms. Everything was plant or animal. Okay, so that tells you how old I am. Everyone believed that everything was a plant or an animal. Okay, problem with that is, for 100 years that idea didn't fit, but they just stuck with it. Okay, it was the same idea, it was the same mentality of a small child forcing a puzzle piece into a spot it doesn't fit in. Okay, they crammed fungi into the plant kingdom. Okay, they grow out of the ground, so they're plants. It doesn't matter that they don't do the key thing all plants do, carry out photosynthesis. Okay, kind of an important distinction, right? But for the longest time, people resisted making the change. Okay, now everything falls in 5 kingdoms instead of 2. Okay, we got plant, we got animal, okay, we got the protists, okay, we got the monorins, plant, animal, and the fungi. Yeah, fungi have their own kingdom. Okay, 5. And so we have to change our models and our ideas as we discover new things. Okay, what are the 3 parts of the atom? We've already mentioned them today, but what are they?
The proton.
Proton. Okay, where do I find a proton? In an atom, it'll be in the nucleus. Okay, and it's positively charged. Okay, and then we would have also in the nucleus neutrons. Okay, and then the last one, of course, is electron. Okay, it is in the cloud, and it is negative. Okay, just as long as you know that, that's part of what we worked on at the very end of the day on Friday, drawing a picture of a particular atom. Know what everything is, know where you can find it, what its charge is. Okay? All right, if I have the same amount of lead, let's say not even like a cubic centimeter, not the same volume. Let's say I have exactly the same number of lead atoms in a pile, okay, and the exact same number of carbon atoms in a pile, okay? Why is the lead so much heavier?
The amount of protons.
Yeah, the atoms are bigger, okay? Like the nucleus of a lead atom has 82 protons, okay? Whereas carbon atom only has 6, okay? So it's naturally going to be heavier. There's more to a lead atom than a carbon atom. Okay, nuclear reactors use atoms with very large nuclei, like uranium that has 237 particles in its nucleus for fission, okay, or splitting of the atom. Why wouldn't they use smaller, less dangerous atoms? If they're less dangerous, what will they not produce as much of? Did you sign in at the office? Okay, thank you. Why wouldn't they use, what is a smaller atom going to have less of?
Explosives?
Yeah, less energy, right? The bigger an atom is, the more energy is required to hold it together. So when you break it, it lets off a lot more energy. There's also this problem of big target, okay? Hitting an atom of uranium, okay, versus an atom of lithium is the difference between hitting the bullseye that's taped to the side of a barn, okay, at 100 yards, or hitting the barn at 100 yards, okay? Like, we're talking it's much easier to hit a big atom and split it than it is a small one. Okay, making sense? Okay, we talked a little bit about this one already. Atoms are indivisible. Why was this statement believed for so long? Because you couldn't do it. Okay, we believe lots of things we can't do. Okay, people believe there was an invisible wall in the sky called the sound barrier that wouldn't let us go any faster than 300 meters per second. And then we did, and then it wasn't such a big deal anymore. Okay, once we learned to split the atom, oh, suddenly it is indivisible. I guess we were wrong. Okay, that's kind of how science goes. Okay, we still have to have that technology. Did I diagram how a reactor and a bomb work? Okay, so with a nuclear reactor, okay, you have a fuel rod. Okay, embedded in that fuel rod are fuel pellets, bits of enriched uranium, so concentrated uranium. Okay, you lower that fuel rod into a big pool of water, and then you shoot alpha particles at it. Okay, they hit the uranium and break the uranium atoms, and pieces of uranium will go off and break other atoms. Okay, and that releases a lot of energy, which boils the water. The steam turns the turbine and generates electricity. Okay, so you have to have, fairly high technology present for something like that to work. Okay, if all the water evaporates, then you have a problem. Okay, that's like a meltdown waiting to happen. Okay, in a bomb, we don't want to be able to control the reaction. The fuel rod allows us to control the reaction. We simply, reduce how much particles we're firing, or we raise the rod out of the water. Okay, either way, we can slow that reaction down. In a bomb, okay, if you've seen Oppenheimer, okay, I don't know if you have or not, okay, but okay, in a nuclear bomb, a fission bomb anyway, what you do is you actually have one small explosion and then the big explosion. Okay, so what you have is a shaped explosive charge, so TNT or plastique like C4 or something like that. Okay, and it's arranged so that when it's detonated and it explodes, particles are focused inwards towards the center, where a big chunk of fissionable material, usually plutonium, sits. Okay, that explosion then causes the plutonium atoms to start splitting. Okay, and then it's a chain reaction that is uncontrollable. It will just go. Okay, until all of the plutonium has been used. Okay, so that's mushroom cloud and death and destruction. Bad stuff. Okay, that's on a very simple level how a nuclear bomb works. It is obviously far more high-tech than that, okay? But at its core, that's what it is. Okay, so either way, we need to be able to break the atoms of these fissionable materials, okay? And we say fissionable materials, we're using large atoms that are unstable already, okay? Uranium and plutonium are already radioactive. They're breaking down on their own. All we're doing is accelerating the process, okay, by what we're doing. Okay, from what you know of the structure of the atom, how do you think the atom stays intact? Why do the electrons not fly off or the protons separate?
opposite charges attract.
Exactly, yeah. Opposite charges attract. Okay, so the electrons are attracted to the nucleus. And remember, electrons are small. It is always the smaller mass that does the moving, okay? Like the moon orbits the Earth, not the other way around. They actually orbit a common point, but you get to that in physics 20. Okay, but for all intents and purposes, like the Earth orbits the sun. The sun is bigger, the Earth is smaller. The smaller object always does all the moving. Okay, so in the nucleus, you have this like strong interatomic force, okay, that is an electromagnetic attraction between protons and neutrons. When you're the most purely positive particle in existence, a proton, a neutron looks negative by comparison, okay, and so they will stay together in the nucleus. Okay, and then number 12, that was the last thing. That has to do with the electron cloud model. Okay, the glow-in-the-dark materials in plants. Okay, we said that when energy is put into an atom, the electrons will start to move faster, and when they move faster, they'll jump. Okay, they'll jump from a low energy level to a high energy level. We call that a quantum leap. Okay, and they can make a couple of those. When the energy is gone, so for a plant, the sun goes down, then those electrons can't stay up there anymore. And when they fall back, they release the energy that they gained. And when they release that energy, it can be used to do other things. In the case of a plant, it is used to separate carbon dioxide and water and put them back together as glucose, photosynthesis. Okay, everybody with me there? All right, any questions on those? Okay, so make sure you've got something written down for all of those. That'll be good study material, okay, for part of your quiz at least on Friday. Okay. All right, we are going to start looking at ionic and molecular compounds, and we're going to do a little bit of naming and writing of the formulas. So some of this, or most of this, should seem familiar to you, okay? If it doesn't, well, then you'll pick it up, okay? But we're going to basically today probably just look at stuff that you're familiar with. Okay, so key points for today. Okay, first off, be able to identify a compound as either ionic or molecular. Okay, and be able to write the formulae, that's plural for formula, we don't say formulas, okay, okay, and proper names for chemical compounds. Okay, what makes up an ionic compound? What's in an ionic compound? Anybody remember from last year? Yep.
When a metal and a non-metal react.
Right. Okay, so an ionic compound always contains a metal and a non-metal. So that means something from the left side of the staircase. Okay, this is the staircase here on your periodic table. Okay, so anything left of the staircase is a metal. Anything right of the staircase is a non-metal. So an ionic compound has one thing from each side. Okay, at least one thing from each side. Right? A molecular compound is made of two non-metals. So anything in a molecular compound, the only things you would see would be this small portion of the periodic table over here. All right? Because of that, they are structured quite differently. They behave quite differently. And they have different rules for writing their formulas and writing their names. Okay? All right, so ionic compounds occur when metal and a non-metal react and combine, okay, because that was one of the things that Dalton said could happen, to form a new molecule. Okay? In these molecules, electrons are typically lost by the metal and gained by the non-metal. Okay? I'll explain that in a minute. would say that that stuff that's underlined is the most important stuff on that slide. Okay, remember, you always have access to the complete notes package on Google Classroom, okay, so you don't necessarily need to write everything that's on every slide. So, ionic compounds, or rather the structure of ionic compounds, is one of the reasons that we still sometimes cling to Bohr's planetary model of the atom. Okay? Because it kind of explains what happens with the electrons when an ionic compound is formed. Okay, so there's this little blurb in there about elements having full electron shells. So I'm going to kind of diagram that for you. Okay, it's not super important, okay, but just so that you kind of see what I mean. Okay, can I scroll up to some blank screen, or does anyone still need to write? Okay. So, according to Bohr, okay, a sodium atom would have its nucleus. Okay, and in the sodium atom's nucleus, there would be 11 protons, and there would be 12 neutrons. Okay, and there would be 11 electrons surrounding the sodium atom. Now, according to Bohr, okay, the energy levels were fixed. So the first energy level can hold 2 electrons, okay, and the next energy level can hold 8. Okay, which only makes 10. So we need how many more electrons? 1 more. Okay, which means that the outer energy level, or shell, of sodium has only 1 electron in it. But it can hold 8. Okay, now, all elements want to have their outer shell full. Okay, so sodium can go about getting this outer shell filled in 2 ways. It can find 7 electrons, pick them all up and stick them in the outer shell. Or it can find somebody to dump the one that it has in its outer electron shell on. Which would be easier? Finding a way to dump 1 or finding a way to pick up 7? Dump 1. Okay? Metals are like that. Metals typically have their outer shells less than half full. So it's easier for them to dump the electrons than it is to find more. Nonmetals are the opposite. Okay? Nonmetals typically have their shells nearly full. So it's easier to pick up 1 or 2 electrons, or even 3, than it is to find a place to get rid of 6 or 7. Okay? So that's why metals and nonmetals get along so well. Okay? They each have kind of what the other needs. Okay? Sodium needs a place to get rid of this electron. Chlorine would be happy to help. Okay? In the nucleus of a chlorine atom, okay, there should be 17. 17 protons. Okay, and 18 neutrons. Something like that. Okay, and then of course chlorine's first shell would have 2. Okay, its next shell would have 8. Okay, and then its next shell would have 7. Okay, to be happy, chlorine needs 1 more electron. To be happy, sodium needs to get rid of 1. Match made in heaven. Okay, they each have exactly what the other needs. So when they bond, they form what's called an ionic bond, a trading of electrons. Okay, now that all sounds great, but these bonds are very weak because, and don't take this from like a sociological perspective, but once they trade electrons, what do I need you for? I got what I wanted. Okay, I don't need you anymore. And so they break very easily. Again, don't take that in a sociological perspective. This is chemistry, okay? This is not how we treat people, okay? But this is how ionic bonds work. Okay? Once the electrons are traded, then you've got two charged particles, two ions, who each have their outer shell full. Okay? This is why, typically, ionic compounds will dissolve more easily in water than molecular compounds. And when they do that, they split. Okay? As soon as salt dissolves in water, you now have a mixture of water, and in that water you have positively charged sodium ions, and you have negatively charged chlorine ions, because this electron, okay, has now gone to chlorine. So now, chlorine has 18 electrons and only 17 protons. So it has a charge of -1, because it's got one more electron than it has protons. Sodium's the opposite. It now has 10 electrons, but it has 11 protons. So it has a charge of +1. If you look on your periodic table, okay, you'll see, at least for the metals, that the charges are all listed. Okay, sodium is a +1 charge. When it goes into a compound, okay, an ionic compound, it'll have a +1 charge. On this side of your periodic table, you don't see the charges written for the non-metals. But if you take out your periodic table right now, I'm going to show you a little trick. Okay? If you notice, everything in group 1 is a +1 charge. Everything in group 2 is a +2 charge. Everything in group 3 is a +3 charge. The reverse is true on the other side. Okay? Everything in group 17 is a -1. So you could write a -1 at the top of this column, and it'll apply to everything in that group. What would the charge be in 16 then? If this one's -1, this one will be -2, and the next one will be -3. Okay? Beyond that, it's a little less consistent, so we'll just go that far. Okay? So that's the number of electrons that would be gained or lost. That's the charge that that particular ion would have. Okay? And that's why other compounds would have different formulas. Like this is obviously just NaCl. But if we looked at, let's say, beryllium, if beryllium goes with chlorine, we'll have to have 2. Because beryllium's outer shell has 2 electrons in it. It's got to get rid of 2. Chlorine can only pick up 1 each. So we need 2 chlorine atoms in order for it to go. Okay? All right. So what you need to know about ionic compounds is bonds are weak, the electrons are traded, charged particles are left behind. And metal, non-metal. Okay. When it comes to naming, what would I call this stuff? NaCl, what would I call that?
Salt.
Okay, that's the common name. What we'll learn this year, and that's totally true. Okay, what we'll learn this year is that salt, in chemistry terms, actually means any ionic compound. All ionic compounds are technically salts, because a salt is a crystalline solid, which table salt obviously is. Okay, so what would be the technical name of that stuff? Sodium chloride, right. Okay, this stuff would be beryllium chloride. Okay, this stuff here, calcium iodide. Okay, are we seeing a pattern to the naming here? Okay, we name the metal first. We don't change its name at all. We just read it off the periodic table. And then we write the name of the non-metal, but we change its ending to I. Did we use any prefixes in any of those names? No. Okay, we never use prefixes in the name of an ionic compound. Okay, here's why. You don't need to. there's only one way calcium and iodine can go together and have their outer shells full and be happy, and that's that way. Okay, there's only one way those charges will be balanced, and your drop and swap, if you've learned about that, will work. Okay, so you don't need prefixes. When calcium and iodine together, that's what they look like. Okay, there's no other way for them to go together. We need prefixes for molecular compounds because they don't trade electrons, they share them. Okay, there's like 4 or 5 different ways that carbon and hydrogen can go together. Okay, or nitrogen and oxygen can go together. There's a whole bunch of different ways. So we have to put prefixes in to say it's this way. Okay, but we don't need prefixes on ionic compounds. Is that ringing a bell?
Yes.
Your phone's in the pocket? Your phone is in the pocket? Okay, cool. Okay, so when we're naming binary ionic compounds, this you would have done in Science 9. Okay, so the name of a binary ionic compound is the name of the metal first, okay, and the name of the non-metal with an "-ide" suffix. Okay, so as I said, this is something you probably would have learned to do in Science 9, so it seemed pretty familiar. There are a few things we're going to add to it, okay? We always throw a monkey wrench into the machine, okay, just to keep you, learning, keep you learning new stuff. Okay. Anybody need that one anymore? Okay, a couple of things about chemical names, okay? Remember to obviously name both parts, right? And names are never capitalized, unless of course you're starting a sentence with, like, sodium chloride tastes great on my French fries, okay? Then of course you would capitalize the sodium. But these are not proper names, okay? Like, John Smith or Jane Doe, they're not a proper name, okay? So they don't get capitalized as a result. So when you're writing a sentence, or you're just writing the name on a worksheet, it should not have capital letters. Okay. Ionic compounds will have a net charge of 0. Right? That means the positives and the negatives have to add up to 0. Okay? So if we're looking at, let's say this one here, aluminum chloride, we see on the periodic table that aluminum has a +3 charge. Okay? Right here. But chlorine, as we said with all things in group 17, is a -1. That means in order for aluminum and chlorine to be together in a compound, there have to be 3 chlorines there to accept the 3 electrons that it wants to give up. Okay? Everybody with me on that? Okay, that's why you do the drop and swap when you make compounds. That rings a bell from last year. Okay. All right, another thing. On a quiz or a test or an assignment, spelling counts. You do, after all, have a periodic table there that you can refer to get the actual spelling of everything. So there's really no reason to not spell things correctly, okay, when you can just refer to the periodic table to get the correct spelling. Okay? The most common mistake I see, okay, with naming compounds is people obviously not referring back to their periodic table. Okay? I know you'll probably get pretty confident in it and feel like you've kind of got it all memorized, but always double check. Okay? You would hate to make a foolish mistake that could have been avoided by simply turning the page. Okay? All right. I want you guys to write the names of those four. Write those down, and then write their names beside them. Let's see how much we remember from last year, and then we'll go through them together. Okay, so if we're following the naming rules for that one, we name the metal first. Okay, so sodium, and then we name the metal second. Put an "ide" ending on it, sodium chloride. Okay, what would the next one be? Potassium fluoride. Oh, other way. U first. Right? See, I should look at the periodic table. I always spell that one wrong. It is the U first. Otherwise, I spell it fluoride. Okay, potassium fluoride. What about number 3? Hydrogen iodide. Which one's the metal? Hydrogen. Yeah. Now this is a bit weird because hydrogen can actually act as a metal or as a non-metal. Okay, it will do both because it has one electron in its outer shell. It can drop it and have no outer shell and be happy, or it can pick one up and have a full outer shell and be happy because that first shell only holds 2 electrons. Okay, so hydrogen very often kind of plays both sides or goes both ways. Okay, here's how you tell whether it's acting as a metal or a non-metal. If it's listed first, it's acting as a metal. Metals are always listed first. If it's listed anything other than first, then it's behaving as a non-metal. So as an example, this would be hydrogen acting as a gas, as a non-metal. Okay, and that would be accepting electrons. Here, it's giving its electron away. Okay, this is actually iodic acid or hydrogen iodide, so it's a very strong acid. Okay, hydrogen iodide. Okay, what about number 4?
Calcium bromide.
Calcium bromide. Do we need a prefix? No, it's ionic. That is the only way that calcium and bromine can go together. All right, now, here's what I want you to do. Look at your sheet. And how many of those did you capitalize? Because it can be a tough habit to break, okay? We're taught all through school, names are capitalized, names are capitalized. Remember, you gotta remember, these are not names, okay? Now, I probably wouldn't mark it wrong if you capitalized it, but I would make a note beside it going, no capitals, okay? Just want you to get in the habit of not capitalizing those names. Okay, let's try a few more here. Okay, let's go up to number 10. Okay, so for number 5, what would we have there?
I don't really know what's in the second part, but aluminum, phosphate or something.
Yeah, some of them are a little tricky to figure out where to cut it off and put the "ide." Okay, for astatine, it's acetatide is usually where we draw that line. So this would be aluminum acetatide. Okay, and yeah, I'm still going to pronounce that the old way because I'm old and stuck in my ways, and I just can't pull off aluminium. Okay, it sounds awesome with an English accent, but it sounds so proper and awesome, but I can't say it that way. It just doesn't sound right coming out of my mouth. Okay, all right. Number 6. What would we have there?
Cesium sulfide.
cesium sulfide. Okay, no prefixes needed. Remember, it's still an ionic compound. Okay, what about number 7? Sodium oxide. Good. Okay, what about number 8? Okay.
Barium selenide.
Barium selenide. There's actually 2 ways you could write this. You could write, whoa, look at that, I went to a capital letter. Barium, you could write it as selenide. That's the way I write it. But this is also correct. Barium selenimide. Okay, either way is fine.
Okay. I like the short way. Less right.
Okay, so selenamide or selenide, either one is fine. Okay, what about number 9? Ollie, what's number 9?
Radium telluride.
Radium telluride. Good. Okay, and
Lithium fluoride.
lithium fluoride. Okay, how are we feeling about these? Okay? Feeling familiar? All right. What if, I got a couple more here, but we're going to just skip them for now. Okay? What would you call this? There's more than 2 elements in it, doesn't it?
Sodium hydroxide.
Sodium hydroxide. Okay, now if you look in your periodic table, so everyone can open up the periodic table. Okay, on the top of the periodic table is this rectangle up here. Your table of polyatomic ions. Polyatomic meaning many atoms. Okay, so in here are some other common charged particles. Okay, all but one of them act as non-metals. Okay, if you look, all but one of them have negative charges. Okay, so only ammonium acts as a metal. Okay, all the others act as non-metals. And you can see here, hydroxide's kind of right in the middle. Okay, so OH is a common polyatomic ion. So if you have a compound that starts with a metal, like this one does, but it has more than 2 elements in it, you are looking at an ionic compound that contains a polyatomic ion. Okay, another example could be something like this. That would be lead 2 nitrate. Okay, it has 3 different elements in it. Okay, so it would have a polyatomic ion. And it is perfectly okay to always enclose polyatomic ions in brackets. Okay, there are situations where you have to, like the second one, because I'm going to put a 2 outside the brackets. But you can put any of them in brackets, even if it's just a 1 that we wouldn't write. Okay, so anytime you see a compound that has more than 3 elements, you're going to have to, that starts with a metal, so it's ionic. Okay, you would have to look up in here for partner. Okay, what would this one be? Okay, is NH4 up there? Because that's an ionic compound that starts with a non-metal. Right? Nitrogen's a non-metal. That one can be tricky. Okay? So ammonium, that's the one that acts as a metal. Okay? So that stuff would be ammonium chloride. Okay? We don't change any of the rules. Okay? If this has, we look in here, if I've got hydroxide, I just write hydroxide. The nice thing about using these is that's the name. You don't have to change it. Okay? A lot of them already end in "ide" or "ite" or "ate." Okay? That's, you just write them as they appear in there. Okay? So let's say you had this one. Okay, Mg stands for magnesium. Okay, and CO3, carbonate. That stuff is magnesium carbonate. Okay? Sorry, not magnesium, calcium. Sorry, I'm so far away I can't even see it. Sorry, calcium carbonate. So Ca, so we got calcium carbonate. Don't have to change anything about it. Okay? What about this one? Magnesium sulfate. This time I'm writing the same magnesium that I had in my head already. Okay, so look up Mg, magnesium, then we look up SO4, sulfate, magnesium sulfate. Okay, is that making some sense? Okay, so polyatomic ions are not like super tricky or anything like that. Okay, we just have to look up their name when they're involved. Okay, I'm going to give you guys about a 2-minute break or 3-minute break here within the classroom, just to kind of take a deep breath, collect your thoughts before we move on to special metals. Okay, okay, let me ask you this question. I have this compound, and I have this compound. Are they the same? No. What would I call the first one? Oh, can't use a prefix. It's an ionic compound. Good try though. It would just be copper oxide. What would the second one be called? Copper oxide. See a problem? I once had this problem. I had in my class, okay, 2 people with exactly the same name. Chase, William, Anderson, both of them. They could not have been more different, but they had the same name. I'm sure at some point I screwed up marks. Okay, I'm sure that somebody's mark got in the wrong place because I had to have them put a 1 and a 2 after their name so I knew which one was which. Okay, but it creates a certain problem. If 2 things that are very different have the same name, I could get them mixed up. Like, what if this one goes in vitamins and this one makes you drop dead immediately? I see a problem with that. Okay? I don't want to write a paper extolling the health benefits of copper oxide and have someone take the wrong stuff. Okay? It's a big problem. So we got to have some way of telling these 2 compounds apart from each other with their written name. With the formula, it's obvious. I can see that they're different. But if I'm writing out their names, I have to have a way to call them different things. Okay? This is where a Roman numeral will come into play. The reason that both of those can exist is because copper is what we call a multivalent metal. That means it can fill its outer shell more than one way. It can drop 1 electron, or it can drop 2. Okay? Making some sense? Right? So you can see there's a whole bunch here. Right? Almost the whole middle of the periodic table is filled with metals that have more than one possible charge. Anytime a compound involves a metal with more than one charge, you're going to have to tell me which charge that metal has. And we do that with a Roman numeral. Okay? So this involves reversing, kind of, the drop and swap. Okay? So according to our periodic table, oxygen is in group 16. Okay? We just wrote on our periodic tables that all things in group 16 have what charge? Negative 2. Okay? So, if oxygen's a negative 2, and a compound has to have a charge of 0, what is the charge on each of these coppers, if there are 2 of them? 1 or 2? 1. Okay? These coppers must be the +1 copper, because if I have 2 of them, that gives me 2 positive charges to 2 negative charges, and that adds up to 0. Okay? If this was the copper with the 2+ charge, then that wouldn't be true, right? this would be, okay, now I've got 4 positive charges, I only have 2 negative charges, and I'm not 0 anymore. Okay, so what you always do is you look at a compound, and you know that there are no multivalent non-metals. So you can always look at the non-metal and know what its charge is. Oxygen is always -2, and there's only 1 oxygen here. Okay? There's also only 1 copper, so that has to be the copper with the 2+ charge. Okay? That way, the compound adds up to 0. Okay, everyone with me so far? Okay. So, what would I call, well, actually, sorry, before I get to that. Okay, this stuff here would be copper 1, okay, so Roman numeral 1, oxide. Okay, this would be copper 2, oxide. All we do is put in a Roman numeral that tells us what the charge is. That way, if I'm given the name, I know what charge to use when I drop and swap. Okay, if I don't have that there, then I'm guessing. Everyone kind of with me there? All right, then, what would this stuff be called? What's PV stand for? Lead. Okay, what's I stand for? Iodine. So this would be lead something, iodide. Okay, now lead has 2 possible charges. Okay, according to the periodic table, it can be a 2 or a 4. Which one is it most likely here? Yeah, most likely the 4. Okay, because iodine has a -1 charge. It's in group 17. Okay, so if I've got 4 iodines and every one of them has a -4 charge, I know I've got to get 4 positives out of this 1 lead. That's got to be the +4 lead. Okay, so this would be lead IV, 4, iodine. Okay, now, in case you don't know your Roman numerals, that means you have not watched Star Wars or Rocky or any of the great movies that have multiple sequels, okay? And you should really make that part of your life because they're both awesome, okay? So, 1, I. 2, I. 3, I. Okay, now here's where it gets weird, and this is why the Roman Empire fell. Okay, it had nothing to do with the Huns, okay? It had to do with their number system. It's silly. 4 is IV. That is 1 before 5, which would make 5V. Follow me there? You're almost never going to have to go higher than 5 for our purposes, but the pattern continues, okay? 6 would be VI, and 7 would be VII, okay? And then you go to 8, which would be V with 3 I's. And then 9 is 1 behind X. X is 10, so you'd have 1X, and then 10 would be X. And we're not going to go any further than that, because you're probably not going to need to know beyond 5 for our purposes, okay? But that's the Roman numerals. Okay, if we're talking Star Wars, okay, these are the good ones. Oh, sorry, I scrolled up on me. Sorry, 4, 5, and 6 are the good ones. Okay, these are okay, and these are garbage. Sorry, did I go on a tangent there? Sometimes that happens. Okay, what would this stuff be called then? If the other one was lead 4 iodide, this one would be lead 2. Okay, it's going to get a little bit more complex than that, okay, when we start talking about it a little bit more tomorrow, okay, but suffice it to say that this pattern kind of holds true, okay, but I will give you kind of one here. What's always the charge on oxygen? -2, okay, it's in group 16. So its charge is always -2. Manganese can be a 2 or a 4, I believe, right? Yeah, okay, can be a 2 or a 4. So if this compound is going to equal out to 0, this has to be the manganese with the 2 plus charge. Okay, so then we would write manganese, Roman numeral 2, oxide. So we still don't use any prefixes. It's just a little bit of math, a tiny bit, okay, that you have to do to figure out those Roman numerals. We will practice that tomorrow. Now, please remember that today you do have an altered bell schedule. That means the breaks are shorter. Okay? Normally, Monday to Thursday, you have 7-minute breaks. Today they are 5. So hustle your butt. Okay, from one class to the next. There's not going to be as much time with those full hallways. All right? Okay, also, if you haven't, make sure you write down those practice quizzes. Probably try number 1 tonight if you've got time. All right, good job today, guys.